Welcome to the second video of Chapter 9. As promised, we continue creating the software project that controls the display.
Let's get started with our software project, which we will show you through a pre-created program. Let's look through it together and interpret it so that next time you can easily put together a project with a display on your own. Load the downloadable example project and open the IOC file. In the Pinout and Configuration tab, you can see the microcontroller's footprint and settings.
The I2C SDA and SCL legs are connected to the pins PF0 and PF1 according to the hardware associated with the I2C peripheral 2. The communication protocol setting can also be seen by opening the I2C menu item, which is as follows.
Other HMIs are also part of the project, some of which you may already be familiar with. For example, we have inserted our 3 push buttons called HMI button 1, HMI button 2, and HMI button 3. For now, do not change the code, let's stick to the original configuration. Let's navigate to the Project Explorer view and take a look at what's new compared to what we know so far. In the core folders Inc and SRC subfolders, you will find files related to OLED displays, which we will now review together. Let's start with OLED conf.h, which contains the user configuration needed to use our display. We can control the display by sending commands over to the I2C bus using the familiar hal I2C memWrite function. This function has 2 hardware-dependent parameters. The I2C handle type def, which is a pointer to the configured I2C structure, and a 16-bit address, which is the address of the target device. In order to make our code modular, we have defined these 2 parameters with the following 2 macros.
The pointer given to the port points to the generated I2C structure, which is in the main.c file. The address is 3C hex as found in the datasheet, which must be shifted by 1 bit during transmission. I understand that our goal as software developers is transparent and reusable coding, which facilitates easy interchangeability and integration of software modules or software components. But why does this make our code modular?
The code is modular in the sense that if we use the OLED I2C port and OLED I2C ADDR macros in the rest of the software, we can quickly handle a possible hardware change with minimal programming. If, for example, we switch our display to I2C on the other leg of the microcontroller, it's enough to change the value of the macro in line 5 and the OLED driver will be compatible with the new configuration. Another example is if we change the OLED display and change its address, we just need to update the macro in line 6 and we can welcome it as a familiar on the bus. Another display-specific parameter is the height and the width of the display. These are used to calculate the size of the array used to map the points on the screen. We can describe a pixel in 1 bit, so the total display size can be represented in 8192 bits or 1024 bytes.
In our configuration file, you can also see that we have the option to mirror the display vertically and horizontally, and to invert its colors.
We can activate these options by removing the comment marks from the define by deleting the double slash characters from the beginning of the line. The defines here are called compile directives, which means that part of the source code will be compiled depending on these options. You will see an example of their use soon.
Am I right to think that displaying letters is not just telling the display what you want it to do?
Absolutely. However, using the prepared library is not much more complicated than that. Let's see what it looks like. Because our display is graphical, we need to control the pixels 1 by 1 to be black or light. If we want to print text on the display, we also need to tell 1 by 1 which pixels to activate for a given character. To do this, we need to create predefined character sets that contain the visualization of the letters. If we want to use multiple font sizes or fonts in our application, we need to create separate font sets for each size and type. Currently, our code supports 4 font sizes. The smallest is 6 pixels wide and 8 pixels high. The largest is 16 pixels wide and 26 pixels high.
In the last code snippet of our source file, we can set which of the 4 character sets should be available in our software. In our example, all of these font sizes are available. If we don't need one of them and want to reduce the size of the code, we can turn it into a command.
Speaking of letters, let's take a look at what the different character set implementations look like. Let's start with OLED fonts .h. At the very beginning, you can see our OLED conf h file inserted, that is, included. After that, a structure definition called fontDef is shown.
This is a structure we use to describe our characters, which has 3 elements: font height, font width, and a pointer to the font. You can see the use of this structure from line 403 onwards in the OLED fonts.c file.
A block with a compile directive should be interpreted as follows. The code fragment between the preprocessor directives if-def and end-if is compiled into the final program if the expression following if-def has been defined before or has a logical value of 1, meaning it's true. Since OLED include font 6 times 8 as defined in OLED conf h and included in this file indirectly via OLED fonts h, line 404, will be compiled into our program. This line does nothing more than create a structure called font underscore 6 times 8 and give it an initial value. We set the width and height according to the name and specify a pointer to our font.
Move the cursor to font 6 times 8 on line 404 and press F3 to jump to the declaration of font 6 times 8.
What do we see here? Firstly, the familiar preprocessor directive should be used here as well. The font 6x8 is an array of 16-bit unsigned integers. The font is constant, so it can be declared as a constant. It is static because we do not want to access this array from another source file. Examining the elements of our array, we can see that each row contains 8 pieces of data which together describe a character. Let's visualize it for easy understanding. Each letter has a width of 6 pixels and a height of 8 pixels, 6 columns and 8 rows. The 8 pieces of data on each line of our code describe the 8 lines of our character from top to bottom. As an example, let's choose the hashtag character, which is the 8th line of our code we showed you earlier. The first element represents the first line, the second element the second line, and so on. The data is 16 bits, but only the top 6 bits are needed, so only the top 6 bits are displayed in the third column. These binary values should be displayed on the left display according to OLED technology, with 0 being black and 1 being white. Then we get the following image, which is a light-colored hashtag on a black background.
Now we know what the lines mean, but what is the basis for the array representing the characters?
The order of the characters was based on the ASCII code table, except that the first 32 characters and the last character were not included in the character set. To better understand the big table and interpret the lines, we suggest you pause the video for a moment.
The question can also arise, why do we use a 16-bit array if only 6 bits are enough for us?
If we look at our character sets, the largest letter size is 16 times 26 pixels. In order to make our character sets compatible, we chose a data type where all font sizes can be represented.
I see. I think we should go back to the end of our OLED fonts.h file for a few more words.
The external keyword tells the compiler that there is a variable somewhere called font 6 times 8 of type fontDef that will be encountered when linking, so compile it for us. In effect, we are offering font 6.8 for use by those who paste the header file. We have 2 files left that are directly related to the OLED display. These files implement the functions that we can use to bring our display to life. Let's interpret each code snippet together, starting again with the inside of our header file as before. First, we include all our work so far in the form of OLED fonts age. You can find the declaration of I2C port defined earlier to point the compiler in the right direction. These are followed by some enumeration types, or enum for short, which make our code more understandable for us. The enums created are as follows. The first component is OLED color. The first element of this is black, which represents the color black. The second element is white, indicating the color of light. Next is the OLED switch. The off position of the switch signifies that it is turned off, while the on position means it is turned on. At the point of use, you will see how easy it is to code and analyze the code thanks to the types listed.
The next part is the definition of two structures.
In the first structure, we find the features of the OLED display that are essential for its basic and proper operation. From the top, the first two elements represent the virtual cursor of the display. These allow you to specify a point on the display, for example, when you want to start displaying text. The remaining elements in the structure are used to keep track of various settings, whether the display invert function is active, whether the initialization process has been successfully completed, or whether the display is turned on.
You could say that these are mandatory to keep track.
Exactly. The OLED vertex structure will combine coordinates for easier handling. At the end of the header file, we find the declaration of the functions that are available outside the module. In this case, we call a module the logically coherent part of the program. The implementations of the functions listed here can be found in the source file, so let's move on to the study. As usual, we start with the includes, followed by the macro-defined constants, then some variable definitions, and finally the function implementations. Two important variables were introduced. The first one is the SSD1306. In this structure, we can store the current states and settings of the display. The next is the OLED buffer. This is where we can keep a local copy of our display. If we want to draw something, we first do it in this map and then send it to the display. At the display level, we can think of this as saving the data sent to it into a RAM memory, which it then displays bit by bit.
And what aspects did you consider when designing the structure of the source file?
Logically, we have built up the source file in such an order that the functions necessary for basic operation are at the beginning and are essential for the display to work. These essential elements are the communication functions that can be used to send commands or data to the OLED module. Both for OLED write command and OLED write data cases, we use the HAL I2C memWrite function for I2C communication, but only change its input parameters. As port and address, the two macros previously defined for this purpose are given the OLED I2C port and the OLED I2C address. The third parameter is used by the OLED display to distinguish between command and data. Information on this is given in the datasheet in section 8.2 command decoder. The fifth and sixth arguments, uint8 tp data and uint16 t size, are also relevant for us. The former is a pointer to the data to be sent, and the latter is the size of the data to be sent. In the case of a command, this is a 1-byte command code which can be retrieved from the display's datasheet. When sending data, the buffer address and the size of the data packet must be specified.
I understand, but let's look at this in a concrete example. What does the process look like, for example, when you send a simple command to the display?
The OLED setDisplay function is used to turn the display on or off. In its trunk, you can see that we set the code of our output command based on the input parameter, on or off, update the state of the display in the register structure, and then send out the set command.
How can we find the codes for the commands?
In the datasheet, chapters 9 and 10 contain the commands and their descriptions. For example, the on-off command is described in the first comment table in chapter 9 and in chapter 10.1.12.
Our function for inverting the display has a very similar structure.
In use, You may need to check the inversion status, which you can do with a query function.
Why not check the SSD 1306 structure in the main program?
Because this structure has been hidden from the main program and can only be accessed through these functions. This solution improves the modularity, that is, if the inside of the OLED library changes, the main program will not be affected, provided that the interfaces of the module remain unchanged. The other argument for hiding the structure is that the library that manages the display must keep track of its own state. Its users are just consumers of this information.
Going back, we can also set the contrast of our display using the OLED setContrast function. You can set your cursor to any pixel of the display using the OLED setCursor function.
We can set the color of the entire screen to black or light using the OLED fill function. If we specify white as the input parameter, we have to set each bit of color value to 1, that is FF. If our input color is black, then the value of color value doesn't need to be changed because its initial value is set to 0. After that, we just step through the output buffer and fill it with color value.
Now we know how to fill the output array with a particular color, but how to pass this to the display?
For this purpose, we have a function called OLEDUpdateScreen, which sends out the contents of the buffer on a block-by-block basis. A block contains 8 complete display lines.
Our ultimate goal is to use the display. But before we can do that, we need to initialize the display and create the drawing functions. However, we will cover these in the upcoming video. Bye!
See you!